and that's going to give us all the advantage here. So I love that. Before we begin, I just want to introduce our great Ks that are helping us today. We have Alan. See, these claps count. These claps count. Nancy. And Patrick. They're going to be extremely important for this session because one of the first things we're going to do is build a Docker environment to do some demos on. So if you have any trouble with Docker, just lay one of them down and we'll assist you. If you don't have Docker on your laptop, we have a couple fallbacks. You could install the dependencies in like a Helm environment, although the Docker environment is highly suggested. And we also have Databricks Community Edition that is an additional fallback. Yeah. So our agenda today is we'll set up our environment to run demos, and then we'll go over a history of the data architectures that came before the Lakehouse architecture and kind of motivate the Delta Lake technology. I find that that's extremely helpful to take a historical context for this because otherwise it seems very similar to like, why is this a database but without the compute built in? Why do we need this? So hopefully that will help kind of give a distinction for how this is different than previous architectures like data lakes and data warehouses and what improvements you can see if you adopt this approach. Then we'll move to some demos using Delta Lake's PySpark-based APIs. We'll cover that there are several APIs available to Python users. Two are reliant on the JVM, and one is reliant on Rust, the Delta RS Python bindings. They both have advantages in different situations. The PySpark based APIs are set up better for scaling. The Rust APIs don't require JVM, which is great. So that's almost enough of an advantage there, although they have a very active developer community, and they've been adding new features and APIs that don't exist anywhere else within the ecosystem, so that's very exciting. Then we'll take a little break for some questions, and then we'll move on to some pandas and Delta RS recipes. And then we'll finish up with a shorter 5-minute question, and then we'll be available after the session, of course. Okay, so this is the part where we start building our Docker environment. This Docker setup was contributed by one of our open source contributors, Andrew Bauman, and it's since been iterated upon by the community. It's really great. It kind of has all the pieces you need to start playing with Delta Lake. The first step is to clone this repo. I'm just going to let people Google and type. And then there's just 3 additional easy steps. And it will start up your Jupyter Lab notebook immediately. Just a quick show of hands. Does anyone not have Docker installed on the laptop? Okay, awesome. Thank you for being very as a backup, if you don't want to figure out how to install and set up Docker right this instance, you can use the Databricks Community Edition. If you Google that, it should be the first thing that pops up. You should be able to sign up and sign in pretty quickly for free. And the alternative to that is using a Conda environment. Once everyone has a chance to kind of grab these instructions, I'm going to switch to the next slide, which will show you how to do this in Conda. So this Docker environment is great because it doesn't just have the bare minimum to run Delta Lake on your laptop. It also has additional great tools for the open source community. It has tools like RO API, which is a Rust project which exposes Delta Lake tables as Rust APIs, and is great for building web applications. It has a whole bunch of other goodies. So After the talk, I'd highly suggest you check out the other tools and utilities that are installed in this. Okay, does everyone have at least the Docker environment starting to build? Does anyone need more time on the slide? A little more? Okay.
Does anybody have questions?
Oh yeah, does anyone have questions while we're building Docker environments? Yes. If you don't have Docker, I'd say the Databricks Community Edition is probably the best fallback. So if you do Google Databricks Community Edition, it should be the first thing that pops up. It's pretty quick to sign up, get a new credit card. Really easy. It's a little bit slower on setup than this, so if you give Docker. And also if you need help from a TA. Oh, we have someone who needs help. Quick show of hands. Does anyone else need this slide? That's okay. So if you're in Congoland, this would be kind of the quickest way to set up the Conda environment. Slightly more steps, but also fairly easy. Okay, quick show of hands. Is anyone using this slide to build a Conda environment? One. Okay, cool.
Seems to be going quite quickly.
Awesome. Okay. Do you need this slide any longer? A little bit? Okay. And also, if you have any questions not related to building, feel free to shoot. Yeah.
Can you go back to the Docker just so I can take a picture of it?
Oh, sure. You know, actually, that's a great idea. If people want to take pictures with their phone, then we can progress. And just flag me down or one of our TAs if you need additional assistance. Oh. If you guys navigate to go.delta.io, these instructions are also there.
Go.delta/docker.
Oh, /Docker. My apologies. Okay, so the whale has got its photo op. Does anyone need to take a picture of the conda instruction? Awesome. It'll take a while, so don't worry if it's still building. That's why we just wanted to start it at the beginning.
I think the Wi-Fi is still a bit.
Yeah. That's okay. We have plenty of time before we get to the part where you need it. That you want to rip the Band-Aid off, give the whale and the crab their dues and their love, adoration. We won't see them again for a little while, so gotta get that done now. So yeah, why Delta Lake? A historical perspective. It starts back in the 80s and it goes into the future, which is very exciting. But first, back to the past. The punch card?
Yeah, he's calling out, like, you technically have the punch card.
These others that see us
Right,
do it.
right? 1970? 1960?
Oh, yeah, you're right.
I'm with you, man. I got you covered.
Sorry, you're keeping me honest. Yeah, so like in the 1980s, there were many things, but there was also data warehouses, and they were extremely useful. They covered all the use cases that we wanted. There was no problem. It was great. We could do our ETL pipelines and go directly from our operational databases right to our data warehouses. We had neat, tidy tables. And we could do our business intelligence and report generation off of them. We knew how to do relational databases. It was great. They were purpose-built for SQL analytics. They had indexing, caching, all these tricks to be really efficient. And they had powerful management features and had provided great things like asset transactions and time travel if you made a mistake. So life was good. Moving on to 2018, there's this Candle Data Science survey, and I think it starts to reveal some cracks, which, honestly, from the 80s, that's a pretty good run. This was a survey that asked data scientists, select any of these activities that, prominently feature as part of your job. And you can select more than one. That's why, it sums over 100%. And the responses were, we analyze data, we build ML services, and we run data infrastructure. And so we start to see that these prominent things that a lot of people are doing start to fall outside of the model that we had. And so there started to be cracks. And we needed to start finding solutions. We had more different types of data. As you go past a certain point, relational databases were harder to scale. And so people started to feel the pain. We couldn't support this rapidly growing unstructured and semi-structured data sources. We had time series, logs, images, documents, audio, video, and then it just became very cost prohibitive. Even if you can scale your database, relational database system, it's expensive. So we wanted something that was cheaper, that could still fill the same role, and hopefully support data science and ML workloads. One big problem with these warehouse systems was that you couldn't really do data science or ML inside of them. You had to take your data that was stored within them, and you had to pull it out, and that added overhead and costs every time you wanted to do some work. And also now you have a copy of your data outside of your warehouse system that now can become out of sync. So then we had data lakes to the rescue, 2010. This addressed a lot of the problems we had. It was cheap. That's why it's most important. That's why it's at the top. Don't worry about ease of use. It's inexpensive. We love this. It's a model that could be run on any of the common cloud providers. It's allowed us to load specific data into our warehouses that make sense to be processed there. but still have the flexibility of storing our videos, our audio, our unstructured data, our text, and have it available for ML workflows. It was directly readable by those ML libraries because it was just files sitting in object store. Super simple. But it wasn't perfect. There were some problems. It was cheap to set up, but it very quickly led to complexities in how you would administer this. You had still this arm of your analysis that was still the traditional like data warehouse approach, and you had this sort of messy kind of less regulated, less supported for like management operations, data like blob of data, and so you'd start to get pieces of information out of sync with each other. It was difficult to actually have a system sync this in an efficient way. So all that syncing overhead led to slower operations. That's what these little gremlins represent. All those little inefficiencies. And so with each of these multiple storage systems having their own semantics, all these handoffs and specialized ETL processes, it just allowed for more room for mistakes to crop up. So that's not great. And so the data lake became the data swamp, which I'm sure you've heard of. And then over time, that swamp caught on fire. It was a complete disaster. Didn't even know a swamp could catch on fire. And so as the data sets grew and these data lakes persisted, we had to turn to another solution. So just a quick recap, and don't look at the bottom right, because that's the spoiler, that's the solution. Otherwise, we wouldn't have this talk. We had data warehouses. So great relational database approach, worked great for anything that was in like unstructured or semi-structured. Then we had data lakes. It was flexible enough and cheap, but it was very complex. And so we needed something that was cheap, able to scale for large amounts of semi-structured and unstructured data, and still gave all the benefits of a data warehouse, or at least as close as we could get to something that's purpose-built. Oh yeah, and we also don't want to have to sync across all these systems, because that's sort of the source of this complexity and added difficulty with the data lake architecture. So the solution was Lakehouse technology. So the idea was we'd still have all of our data in object store, in that cheap storage, but we wanted to retain some features of the traditional data warehousing solution. So we wanted better management, better metadata for tracking files, saying which pieces of data were stale, which were like the current versions. We wanted to do things like time travel. We wanted to also eliminate the need for things like messaging queues for syncing between different systems. And we also wanted to build this on open file formats. In the case of Delta Lake, Apache Parquet. This is really important because this sidesteps the issue you have with a traditional relational database, where if you want to do ML or some more involved analysis, you'd have to pull that data out of that proprietary data format into something like JSON or CSV or something that you can actually work on, and then that would perpetuate that syncing problem. So Lakehouse vision is we're going to have everything based off of this cheap storage, cheap, dependable storage, S3, Azure. Thank you. So we want everything to be able to work off this cheap storage, and then we also want to have this metadata layer that tells us which versions are stale, most up to date, and we want to have ACID transactions. We have all these goodies of the warehouse that be able to apply those to things like videos, audio, documents. And that will lead us to a better architecture that pulls us out of this swamp Because if we know what's in our Lakehouse, in our data store, and we can track it, we can maintain that high data quality. And we can do it without having to manually create ETL systems and messaging queues and processes to sync this. So that's sort of the end goal. So usually where a data lake is just a collection of files, a lakehouse is adding that metadata layer. And that's exactly what data lake is providing. It's Parquet, that open file format or on object store, but with additional metadata to tell you, what are the active files, what is currently part of the lake, what is the current version. And that allows us to have better tracking and enables us to have a richer set of management features for our data. And because we know what the active files are, or videos, etc., we can actually skip everything else, and that improves access for clients. So it's also a performance boost to do this tracking that helps us also have more reliant data. So we get a twofer. So here's an example of how a basic data lake would work with a rewrite operation. So we have some events table, and it's stored in Parquet files. And we want to rewrite 1 to be 1B and 3 to be 3B, and we'll delete the previous versions. That way, if a client comes along, it won't accidentally access the wrong version of the file. But the problems the data lake encountered was what the query reads the table while the delete is running, or what the query fails, or what if the query due to the delete fails partway through. That could lead to data inconsistencies. So we need that metadata tracking to avoid these issues. So when we add additional metadata and tracking that Delta Lake provides, we can avoid this problem. When we rewrite the files, we also update a Delta log that's keeping track of all these transactions. It's telling us what is the current version of the table. So in this case, we have multiple versions of the table, version 1, 2, and we're making 3. And we'll track which of these Parquet files is associated with each of those versions. So we say version 2 is 1, 2, 3. And when we do this rewrite and delete operation, we're basically just going to, instead of actually physically deleting the files, we're just going to make a new metadata entry that says we now have a version 3 that uses 1B2 because those records weren't changed, and 3B. So now our Delta table has 5 files and 2 versions, but the client will always read a consistent table version. So before, if something failed partway through, you could read inconsistent data. But here, the client will actually go to the transaction log and see what versions are available. And that log won't be updated until all those Parquet files successfully writes. And because we weren't deleting the previous files as we were writing the new files, and they're both there, we can roll back to the previous version if we need to. In addition to having that safety inherent within the operations that you're performing on your Delta Lake, there's other great management features that are afforded to us when we add this metadata to our normal data lake. We have that time travel to versions, but we can also do a zero-copy clone of our table. Because of the table is the Parquet file is the actual data itself, plus the metadata that's pointing to some collection for each version, we can just clone that transaction log and have a separate set of pointers to the Parquet files, and then we can operate off of those. we can describe the history of the table because it's just reading that transaction list. So we can say version 1 had these parquet files, then version 2 has these, et cetera, et cetera. It's very easy to read through how the data has changed over time. And then we also have all of the normal operations that you expect in a data warehouse, like insert, delete, and merge, which are possible because we have that asset guarantees, and we know that we are not changing anything without being completely succeeding. Okay, so show of hands. Whose Docker file is still building? Cool.
It's a little over halfway done.
Oh, fantastic. I think that's a great time to talk about this very colorful slide and then open up for questions. I mentioned kind of way back, even before you started building that Docker file, that for the Python community, there's 3 great APIs for Delta Lake. 2 of those are sort of PySpark-based APIs, and one is just PySpark. And the other one is this Delta Spark package, and I kind of colloquially call it like the PySpark declarative API. It doesn't have all the operations that you can perform PySpark, but it has a very clean interface for working with Delta tables, and they interoperate. So I think it's worth learning both. And then there's also this newest client, the Delta RS package, which is fantastic. No JVM required, super easy to install and use. It's Python binding Rust, and it kind of just very easily melds with the rest of the ecosystem because it passes information between the Rust and the Python and things with Arrow, which Pandas, our favorite data framing library, also uses on the back end. So it's very easy to very efficiently pass information between them all. Okay, so while we're waiting for things to catch up on the building, does anyone have any questions? Or does anyone need a life preserver thrown to them? And by life preserver, I mean one of our kindly TAs. And we won't throw them, so don't worry. Yes?
How do you deal, I see that you're creating new versions of records that you're deleting, but how do you deal with situations like where you have regulatory requirements to delete user data or whatever that's identifiable?
Yeah, no, that's a great question. If you have, there's I guess there's 2 answers. You can perform an operation to clean up and delete the actual parquet files if you no longer want them there anymore. The vacuum operation would be used for this. There's also a set of patterns for anonymizing or deleting records, cascading off of some other signal. So I'd say vacuuming is the concrete answer, and then there's a host of common patterns to make it easy. One thing you could do is, let's say you have a lot of information by company or clients. You could partition your data by that object that you need to potentially drop data for. And then all those, basically data for each of those entities will map to a specific parquet file. So basically you wouldn't have more than one user or more than one company in a particular parquet file. And so that would make cleaning up those specific files very easy. Otherwise, if you had multiple entities within the parquet file, you'd have to rewrite the parquet file without those members you need to delete, and then delete the old one. Yeah.
Can you explain what you mean by rewrite here?
Oh, so this could be, let's say that these are patient records, and you have in a hospital, and the record says that the patient is currently in the ICU. And they make a great recovery, and so they're discharged. To make that change in the patient's record, you would have to rewrite the Parquet file with that value changed. So you'd be rewriting the whole file, and then you would update the transaction log to point at that new file as the current version of the table. So if the initial version was version 0 of the table, you would rewrite that Parquet file, and then you create a version 1 of the table that pointed to that file instead of the previous one.
So
And
the
that's,
new file, this is taken with the records that were changed to this version?
yeah, no, great question. So the question was, does the new file just contain the rewrited records, or does it have everything that was in the previous Parquet file? And the answer is it has everything that was in the previous Parquet file plus updated records. Parquet files are immutable, which is fantastic, because you know that they haven't changed. But as a trade-off with that, you can't change them. So you have to write a new one. It's not a problem though, because you can perform a vacuum operation not just to remove an offending entity, but you can also do it to remove older versions of the table that you no longer like, or need. I guess you probably don't have strong feelings about the version of the table. You probably like it just fine. And so usually you'll set a retention policy based upon how much safety you want around being able to roll back to previous versions. And then automatically those older versions in that retention policy sets will be cleaned up. Oh, yes.
All the time this transaction logs grow, right?
Oh, sorry, I can't quickly.
All the time this transaction logs grow. The transaction logs which are there under data log, right? They grow. So what happens to the query if the user queries the file, if there is a compaction or something happening within the transaction, what happens? Is it included or maybe use the old transaction logs before we have
Oh, I see what you're saying. You're saying we have bypassed the problem of data getting out of sync or being partially read or written because we go to the transaction log first and then we go to the data itself. And so you're asking, you just pushed the or passed the buck? Yeah, you just passed the buck. What if that happens with the transaction log? So we atomically write new entries to the transaction log. And so when a client goes to read the transaction log, it will only see what's completely written there. And this isn't a problem, whereas it is for very, very large data files, because these are very, very small files. So actually locking for a moment is not expensive. And so what will happen is, let's say you're updating the transaction log and the client goes to read. It will read, let's say, version 0 as version 1 is being written, and it will continue to read version 0 until it's done with its query. And then version 1 of the transaction log will be created, and then the next client that comes to read the table will get version 1, unless they specifically ask for an earlier version. That's a good question. Oh, yeah.
How do schema changes impact the log? Like, if I add a new column to a data set, is it going to go rewrite old versions of that transaction log? Or
Sorry, say that one more time. If
if I go and add a new column to the schema, and someone's reading an older version of the table, the transaction log, will they see that new column, or is the new column effectively another transaction?
If they are reading an old version before the schema change, she'll get the version without the column, so they won't see it there. Okay, show of hands. Oh, great hands, but is it a question or?
Yeah, so I'm wondering, as you keep using this and rewriting more and more, you're going to get a lot of versions sitting around.
Yeah.
When I come to read the data, without posting a bunch of files, the largest version, how do you keep track of what the latest version is?
So by default, you'll get the most recent version, and the transaction logs are numbered, starting at 0 and then counting up, and you'll basically tail the log. So you'll just read like the most recent entry, which will just have like, this is the list of files for version 27 or 10,000 or wherever you are. And that's actually really nice because you're skipping all those other workday files. You're skipping even reading the whole transaction log. Whereas if you were just to do a file list against like S3 or something, that would be a really slow operation. So this is like a really nice performance enhancement. Oh yes.
So is there a danger of, it seems like the transaction log is kind of a critical piece of this. So is there a danger of like a race condition if different users are making different modifications concurrently and the transaction log has to get accessed by different users concurrently? Does my question make sense?
Yes, it does. It's not a concern if you're using Azure or Google Cloud Compute, because our object stores have a method called put if not absent. So basically, they won't accidentally overwrite each other. Basically, the second writer that goes to make the update will see that it's already there, and will throw an error. And then it will have to reattempt. For AWS S3, it's a slightly more complicated story, but not that much. It's a configuration. We configure a lot of stuff. Basically, you set up a DynamoDB instance to act as your locking mechanism because it lacks that API. If you're concerned about costs, do not worry. It is not doing a lot of work here. I think someone recently in the community Slack, which you should definitely join if you're using Delta Lake, says a few pennies for some very large number of checks. So it's sort of a rounding error. Okay, show of hands. Is anyone's Docker still building? A little bit. What does that mean? This is like the old, I shouldn't say old Windows loading things because we're at Microsoft Campus. But it's like the one where it stops at 99.9 and you're just like, I really want to play pinball or whatever right now.
Actually, can I provide some context?
Absolutely.
Okay. So, sorry, there was a question about S3 and all that stuff. So just to reiterate what Jim talked about, when you talk about ACID compliance, basically Jim called out the lack of put of absent. Now, HDFS, ADL should too, and GCS do not have that problem. Now, specific for S3, there is a problem because it lacks put of absent. Now, to give you some context of how often this occurs, we found it. What happens is I apologize if I'm diving too deep into this. Okay. With the transaction log happens, you've got two systems or more systems trying to write at the exact same time. What happens is the JSON file is created, and that's our transaction log. So it's possible in a very small case where two drivers or two writers are going to write just the transaction log. So not the data files, okay? Just the transaction log at the exact same time. Now, what's the likelihood of this happening? Because of this lack of put of absent, is 4 times out of 10 million. Okay, so it's not a common occurrence, but we did catch it. And we caught, and these are numbers I'm giving you from 2017. So in other words, we haven't tested it since because we found it. And so we've been working with the S3 team to actually get that fixed. They promised to fix that 4 years ago. So yeah, so we're still going on that one. So in order to work around that, there's a system called the DynamoDB log store. And so long story short, if you initiate that, then that basically ensures that 4 chances out of 10 million that possibly could occur will never happen at all. So that's the long story short. It's a relatively simplistic configuration. When you configure, you typically will configure a log store within Delta. Underneath the covers, it's actually automatic for almost all these systems. You have, I believe, 3 additional lines in order to initiate the DynamoDB log store for those particular cases. Okay, just wanted to give you that context.
No, that's great context. So you're completely covered. How's that loading bar going?
Final step.
Oh, sweet. Okay. Oops. We'll do that. Any other questions? Because we're
You mentioned that one of the benefits of the data warehouses was indexing. How's that handled? Is that handled by Parquet or?
yeah. So there's a few different mechanisms you can use to speed up queries. It kind of depends on the nature of your data. I foresaw you might ask this question. I have a bonus slide. You've unlocked it. So there's a bunch of different optimizations. One is partitioning. So basically sequester all rows that have a certain like categorical value in one of the columns in the same file. And then that becomes very easy to filter to. Basically what that looks like when you lay it out is there's a folder or directory for each of those partitions. And so it's very quick to just go there, read all the files within that partition. So that's sort of indexing equivalent. And then if you have high cardinality columns, so continuous values, things like that, dates, date times, you can use deordering, which I won't dive into the weeds, but it's multi-dimensional clustering for your data. So basically you can say I have 2 or more columns that have continuous values that I want to be co-located. So maybe you want to cluster records in time, but also by age, time and age. So like time when they come to the hospital and the age they are. Because that's a common query pattern or access pattern. This would basically co-locate those records as best you can, because there'll be trade-offs between all those columns. Oh, yes?
Is partitioning and Z ordering mutually exclusive? Can you use both of these?
You can use both. I'm not sure. I actually don't know off the top of my head. Maybe nobody knows. Is there any trade-off to using partitioning and Z ordering together?
Okay, so, sorry, Michael? Sorry, can you hear me? Yes? Okay, cool. Okay, no, you can definitely use both. So the context, if you remember, like, partitioning basically is setting up the file system itself to basically indicate clearly that, like, using date partitions, right? And so Z order basically is an attempt to say, okay, can I go ahead and skip, i.e. reduce the amount of files I have to scan? So by already, let's just, for the sake of discussion, you're partitioning by year, okay? And so you specifically say, I want to look at only data from 2012, right? So then by the very definition, you already can reduce the number of files I have to scan or look for, because I know that I'm supposed to look at the 2012 set of files. Z order on top of that will then go ahead and reduce. I'm saying, okay, well, I know I'm supposed to look at 2012, but I'm also have some predicates that say, like, okay, where, I don't know, product is bikes, okay? So, so then the idea is that the Z order helps you can actually identify within the 2012 set of files which ones that are most likely to contain bikes in them. So that way I can reduce the number of files that I have to look at, right? So pretend you're a sports retailer, you sell a lot of different items, right? By using Z order, I mean, instead of going through 1,000 files for 2012, God, what year were you at? 2022 for last year. The idea is that you can go ahead and basically say, instead of actually looking through all the files for 2022, right? I can say, okay, I only need to look at these 15 files that may contain bike information in it. Right? That's the whole purpose of it. So you can absolutely use both. Now, the only reason I'm saying you can is because theoretically, you can also go ahead and forego partitioning altogether and just do Z order for the whole thing. Okay? You can actually do that, and Z order actually can handle it. Z order by itself can handle it, Spark by itself can handle it. Most other infrastructure is not well designed for that though. So that's why I will not advise you to do it, or at least not yet. Okay? Because even Spark's primary default infrastructure is still to follow high style partitioning. Okay? But Z-order, you can theoretically go do that. So in other words, you could just say, I've got a single table, I do Z-order, I'm done. So, but again, best practice, I would definitely start off with high style partitioning first.
Okay. Awesome, thank you. Oh, yes.
Can you use the order of multiple columns?
Yes, in fact, that's usually how people perform Z-ordering. Because it's a multi-dimensional like clustering, if you just did it on one column, you'd be just ordering the values and then chunking them, which, you know, in some cases is helpful, but usually, like the place where you actually see the benefits for a normal data access, update, delete pattern, more than one column, absolutely. That's the best case.
In performance, it's you use more columns in the order like.
Yeah, that's a great question. So the question was, you know, if it's best to use the ordering when you have more than one column to search across efficiently, is there some diminishing return that, in the extreme, if you use the order by all the columns, what would happen? And yeah, there definitely is. So the more columns that you deorder by, eventually you get to a point where the constraints you're putting on, like laying the data out, kind of loop the clustering. You can kind of think of it as like a curse of high dimensionality almost. But if you usually will have, some fraction of your columns for to cluster on, so you're almost certainly going to be good. But always has. Okay, any lingering Docker file builds? Can you give me a comment? I got a fist bump. That's great. I like that energy. That's what's going to make us be the winners at clapping at the end of this. Really show those people their place in the conference. Yeah. Okay. Very good. Well, oh, actually, I should go back to this slide really quick. So if you have your Docker image built, then you should try running it to pop up the environment. If you're not familiar with Docker, what we're doing here is we're creating a container off of the image, which will run all of our software. And we're not mounting it to our actual laptop's file system, so anything you do in here will be erased. So it's ephemeral. If you want to make whatever you type in your notebook persistent, you can add a -v for volume mount, but you also don't have to worry because we'll upload these notebooks somewhere for one afterwards as well. So don't worry too much. And then the -p is to bind the ports of the container to your laptop so you can see the Jupyter Lab notebook. Control equipment. Okay. Let's give her a second. And raise your hands if you have any trouble starting your container. Oh, we have one. We're going to dive into creating a Delta table and then inspecting that transaction log. So you guys asked some great questions, which are great because it's like I planted you. I get to answer them with code and pictures. No, you're not supposed to. You can create a blank one, and then we'll be tagging along with this. I just didn't trust myself to live type as I talked. I'll zoom in so it's easier to see and read. Oh yeah.
Are these notebooks also available somewhere, or
Um,
do they run in the container?
They all will run the container. These specific notebooks, I'll post them like after the talk. So I think these are all going on YouTube. So I think we'll just add it to the description. Yeah. So this is our kind of model for a delta table and a transaction log. Each of these version marks are a different version of our delta table. And we have different data sets here because the table is changing over time. So we're going to kind of replicate this with our PySpark API. So if you're using the Docker container, Spark should already be in your environment and configured. So you'll be able to use it without import. And we'll just make a very simple ID data frame. And then we'll repartition it to one, to be one partition. And this isn't a delta-like partition, this is a Spark partition. And this is just so that when we write out our data frame, it's all in one Parquet file. So normally you wouldn't add this. This is just so that we have it all isolated. So the way that you write a data frame out as a delta table is you would write, format, and then add delta, and then save. So it's very simple. If you've been using Parquet in the past, it's a very easy drop-in replacement. And then if we look, there we go, refresh our file viewer, we see that under temp, some nums, we have our delta table, which is a Parquet file, so that open storage format that we can read directly for an ML application or some other application without having to actually, do some ETL process to extract from some proprietary data format. And then we also have this delta log or the transaction log. So if we click in here, we see .json. So this is the first version or version 0 of our table. And this is the first log. So if we open it up with the JSON editor, it will error. It'll be angry because it has an unexpected character. I think it's just a new line. So we'll open it with the editor, which is just a plain text editor. And we get to see what the delta transaction log actually looks like. So at the top, we see this protocol entry. And this is basically telling us what version of the reader and writer we can use on our table is compatible. So the delta specification is updating all the time as new features are added, new optimizations. And so a reader needs to know, what features are available, is compatible. So we have some information around that. And we also have some configuration information. So like right now, all Delta Lake tables have Parquet as their data format, but written into the specification is the opportunity to, in the future, use something other than parquet. And then we have information like the name of the column, in this case it's ID, type long, it's our schema. And then we have this first record, which is actually adding and making that initial Delta table version. So it's adding our parquet file. And then it gives us information around the size of the data, modification time, number of rows, and then the version number. Sorry, 1 second. There we go. So switching back to the notebook again. And make a second data frame. And we're going to append this to our Delta table. So here instead of, here we'll actually add a write mode for append. You can also have an overwrite, in which case it would replace the table with this new data frame, but we're just going to add these records. And then we're going to look back at the Delta log and see what's changed. So before we go to the Delta log, we see that a second parquet file has been written, and that will contain those added records that we appended. And then we see that there's a second entry in our Delta transaction log, which is this JSON number 1. So let's open that up. So it has an add action, and it's adding that other parquet file that has the new records. It also gives us the size and modification time. It says data change, that's great. And it also gives us some operation metrics, which are helpful. It gives us the number of files that were added, the number of output rows, so we added 3 rows. So it records that we've added 3 rows here, and the number of bytes. So this is nice if you want to go through and see a record of like how the data was added, velocity, kind of spike. You could go through your transaction log and get that type of information very easily. You view this nice structured JSON, which is also APIs within Delta Lake to parse. Oh, sorry, I can't quite hear you. Oh, yes, absolutely. Here it is. So the difference between the first write command and the second one is we've changed it to mode append. Whereas before we didn't need to specify a mode because it was the initial writing. Oh, yeah.
You mentioned before, so that version only contained a new file, not the previous file. And then like, version 0 actually no file wrote, version 1 only one file wrote. So if I want to leave back out, I have to be both of them to figure out the whole file.
So there's different actions in the transaction log.
Okay.
So there's like add, which we've seen. There's also delete, which is just removing it from the active records. And the way the transaction log will kind of evolve as you interact with the Delta table more and more is it will add additional JSON records up until it hits 10, and then it will compact them into a parquet file, which kind of describes the history of the table. And so that's a lot faster and more consistent to read. Otherwise, the reader will, let's say like you haven't hit that checkpoint. actually checkpoints are really over, it is a checkpoint, but sorry, words. Let's say you haven't hit that point yet. It will read all the JSON records leading up to that. Or let's say you've hit one checkpoint and you've done 2 or 3 more JSON records. It will read the most recent parquet that has the whole history. And then we'll read the additional JSON to get the most recent changes. So that's a really nice optimization because parquet is very quick and easy to parse. The reason we don't write out parquet for everything and we use JSON is it's faster for just a few records to just put out JSON. You evade that compression, decompression overhead of the parquet, which for large amounts of data is worth it. Then we'll create another data frame. And this time we will overwrite it. Let's take a peek at our So here we've overwritten our delta table. So if we read it, we'll just have those new records and not the old ones. But we still have all 3 of the parquet that we've written so far. And that's because we have that overwrite operation. We're not actually physically removing those data files, right? We're updating what's considered an active record, part of the delta table in the transaction log. And then that transaction log is pointing to some collection of parquet files that's associated with this version. So let's click in there. Whoops. Oh, sorry. That's a very good point. I will wait just a little bit longer. And if people want to just kind of look up and give me approving looks when they're done typing, then I'll kind of get a feel. And again, the big difference here is that we set mode to overwrite instead of append like before. And we go to the log. Here we have an add action for the new data that we're overwriting with. And then we have 2 remove actions, removing those previous 2 parquet that we had initially written and appended from the list of active parquet files in our delta table. So if a client goes to read the table now, it will read through and say, oh, okay, so we have this parquet, oh, this parquet is added and those 2 are removed. That's the set of parquets I should actually read. So that's how it determines the active records to return for a query. So if you're a client that was reading, you would just play back through the JSON 0, 1, and this one. And then you would be able to reconstruct the state in the history, which is nice. so we've updated our table now, and we've overwritten it. But what if that overwrite was a mistake? Well, don't worry, we can restore. We can go back and we can read different versions of the data, and we can correct our errors. So if we're just going to read the delta table without specifying anything special, we can just do spark.read format delta, and then we can load the location of our table. And a reader will know that this directory is a delta table because it will see the delta log. And then we'll know to enter the directory and start reading JSON and PyData to reconstruct the history. So when we do that, we get the values that we overwrote the table with, exactly what we expected. Then if we wanted to read older versions, then we could pass in an option when we're loading our delta table. We could pass in a version as of, or later I'll show you how to provide like a date time. So if we do version as of 0, we get the initials 1, 2. And the version of 1, we get the delta table after we did the initial 10. And then finally, if we do 2, which is the most recent version, we get the overwritten values. And this is possible because we didn't actually physically remove those Parquet files. They're also there. Delete operations, every operation up until something like a vacuum is just adding more data and like context, which is fantastic. All while keeping it speedy to query because you're doing all this file skipping. Yes?
Cell 11 is backwards from what I expected it to be.
Oh.
I would think it would be 0, 1, 2, and then 8, 9, 10. It does not matter how it was sorted, or?
Yeah, there's no like inherent order. That's a good question though. Yeah, Spark's not about that life. It doesn't play by those rules.
Instead of version as of being an integer, could it also be a date?
Yes, absolutely. Yeah.
Yeah, it's just easier to write.
Yes, this is so much easier.
You don't want to write the entire date timestamp. I was thinking like if you're like time traveling, it would be like the date between. Yeah, exactly. So there's actually a version as of the top.
Yeah.
Like the purpose of the demo.
Yeah, okay.
It's just a lot easier to write version.
I have the call right here, and then we'll go back up and take our time getting back to this point, but I just want to show you really quick. So here we're doing time as of. It gets angry with me because the timestamp I provided is before the earliest version available, that I'd have to type out this whole thing. Like it's not going to accept half measures here, which I respect. Just like Edith will not accept half measures when we clap at the end of this. But like if I just try to give it a year or a day or a day or something, it's still very unhappy with me, which it's not great. And we shouldn't fault it, it just has high standards. But because of that, I usually do the version as of API. It's more accepting of where I am. And even if I put this time for the most recent version, it still doesn't work because it's like, oh, it's still like, spraying on top of it, I actually need, so I actually have to like add a second. Or not a second, in the middle of a second or whatever. And then it will return what I want. It is nice if you have like a very long lived history of your table, and you know that you're trying to like grab something like important to some event, then it's super handy. But for like day-to-day analysis, probably version as of will be more useful. Yeah?
If you vacuum the table, does the version as of change? Like if I'm referencing version 2 and I go and delete versions 0 and 1, am I still referring it to as 2 or 0 now?
Yeah, so that's a great question. So the question was, I've heard of this vacuum operation. I vacuum up the old files. Does the version as of the table kind of like go back? So like, is my version 10, since there's only 3 versions of the table now, is that version 10 now version 3? No, it keeps its version as of. So that's like unique for the table. It'll just keep incrementing. It's just that there won't be a version 0 through, 9 or whatever you backed it up. If you attempt to time travel or read that version, it will of course fail because you destroyed the underlying parquet. But you'll still, maintain a record that it existed. It will always exist in your card. So, life lessons in there somewhere that we don't have time to find them. Okay, so rolling back up to the version as of queries. If we try to query a version that doesn't exist, we get kind of what we'd expect, a nice little helpful error that will say, hey, you haven't done that yet. Come back to me when you have a version 4. But as long as you query a version that exists and you haven't deleted the parquet files for, it will very happily and efficiently return it to you. And then if you want to look at a summary of sort of the table history, there's this very handy history call that you can have on your Delta table. This is actually using that declarative API that I referred to before. So this is what I call the declarative PySpark API. It has what I believe is like the handiest API for accessing this history table. And basically this is a table of all of those JSON records that are in the Delta log. It's very nice to use if you want to kind of get that meta information about how your data set is evolving. Oh, sorry. I'm just so excited. Let's have a little coffee break here if anyone has any other questions about time travel, the mysteries.
So the timestamp, that doesn't have to be explicitly one of these timestamps, it can be something in the range between these?
Absolutely.
Okay. So do you recommend as a best practice, folks kind of query this based on the timestamp or the version?
I think it really depends on what you're using your Delta tables for. So one of the things I love about Delta Lake as a technology, back when I was doing more clinical healthcare analysis at Scalable Children's Hospital, I worked with much smaller data sets than I do today. And so back then, version as of was great because I kind of knew I had 4 versions. You know what I mean? And I might fork the Delta log, do some experimentation. It was very straightforward because I didn't have a lot to juggle in my head. But it still was the exact same approach and architecture and tooling as when I was working with really large data sets, there. So I could use the same APIs and approach and the same time travel helpfulness, but data sets were just a couple of gigabytes to terabytes. And when I was working with things that were more than terabytes, with a lot more add actions involved, time bounded queries were usually more helpful. And when I had a smaller data set with fewer updates, kind of version as of was more helpful. In fact, for smaller data sets, I would just turn the retention policy off completely and just keep the full history. Because storage is cheap, it was just convenient to have the history of my whatever gigabyte data set from its inception. I didn't really care that I had duplicate stuff. It was fine for the scale. So I think it just there's trade-offs, but it becomes very intuitive. What will work best for you in the circumstance. Oh yes.
So in the examples you've given, you created a simple ID frame. How would something like this work with an API, where you're pulling in data based on dates and then
Yeah, so let's say it's like a JSON API.
Yeah.
Awesome. So in this case, you're right, we're kind of like, we've already made the data frame kind of manually, and then we're just kind of shoving it in. But Spark has, and a lot of the other APIs and tooling that you've used to interact with the Delta table, have the methods and parse methods for other data types. So what that would look like is, you have some process that is maybe making the API calls, or is reading like a landing zone with a bunch of JSON up there. And then it would be parsing that JSON into a data frame and then saving that data frame to your Delta table. So in a sense, it's it's a very similar flow, even to this like very simple ID example.
Right.
You just sort of tack on that business logic that you already probably have for like parsing your data. And in the case of common data sets like JSON, there's like super helpful like parsers and like a tooling that will do a lot of that for you.
Okay, perfect.
Okay. Slowly scrolling. Nice. And so just to kind of get a better intuition about time travel in the transaction log, for each of those versions, we're going to have some collection of files, file A. And file A is that one Parquet file that could be a reference across multiple versions. So, version 0 could point to file A that's load to version 2. You're not kind of replicating that underlying data. So that's very nice as far as like an efficiency. And then kind of fast forwarded to this point in the time travel demo, but you can also do time as of. And then I mentioned that like as you do more and more transactions, it starts to become inefficient to use JSON as your sole method for updating the Delta transaction log. So I just wanted to demo the creation of one of those checkpoint files. Really doing that data creation. And so then if we click in here, we see all these additional Parquet files because we've done a bunch of overwrite operations. We haven't deleted anything. And then if we go into our Delta log, we now have some additional things other than JSON. We have this checkpoint Parquet 10, which will have all the information of the JSON 0 through 9, which is 10 JSON. And then every time we hit an additional 10, we'll kind of compact that whole history. That way, a reader just has to check out one compressed Parquet plus or minus, or plus 0 to 9 JSONs, or 10 JSONs. And then we have the last checkpoint file pointing to the last checkpoint. Nice. So that's sort of time travel and transactions in a nutshell. I want to go over that vacuum operation as well. And here we have something a little bit more complicated than the IDs. Not much more complicated, but Bob, Sue, they have a name and an age. So there's a lot more going on for them than the IDs. So we're going to make an additional Delta table to practice vacuum. And we're going to do the same write operation here. We're going to repartition to one. You wouldn't normally do that. I'm just doing it so that all of our updates are just in one Parquet file, so it's easier when we go into the transaction log to kind of see what's going on. And I'll write out in Delta format to this temp sub people. And then I'll create an additional data frame with more individuals, and I'll append. And then we'll just read the table back. So now we have our data set of 4 individuals. So okay, now we have a table, it has history. We don't want some of that history. Let's go vacuum up some old versions. So the default retention period is pretty high, especially for a 90-minute demo. So we're not going to wait around here for 100 hours or whatever it would take. So it's going to throw an error. And that's great. This is a built-in safety mechanism. So while you're time traveling around your data, maybe you're still a little bit new to the APIs, or maybe you have someone else working on your team that's a little bit new to the APIs. It's possible that they could accidentally do a vacuum command and not quite realize the gravity of the situation. Port and grid will just be completely whisked away. And so, luckily, the engine will stop you. It'll stop me any minute now. I haven't given my container that much system resources, which...
Well, when you said you go back altogether, this.
Oh, absolutely. Sorry. And also, if anyone has any questions while we're going. Yeah?
I wanted to connect this with some sort of high-level store to keep track of what tables I have written in marketplaces. Is that supported, or do I have to do that?
Yep, that's supported. Hibbard store is supported. Catalogs are supported. Unique catalog, Glue. I'm sure I'm forgetting some others. There's a lot of options. One that starts with an A. That's not helpful to you. But yes, you can you can register the tables so that you can look them up by their name instead of a path. And yeah, I think that's best practice. Oh yeah.
You didn't put it in the Delta package, but was that one of the other?
Yes.
The Rust one?
This isn't the Rust one. Unfortunately, I think I went a little bit too slowly through so I don't think any will be able to get to the Rust examples. But I will include them in the dump of the notebooks. So, and we'll add some additional notes to kind of guide you on your Rust journey. I don't mean to give them short shrift. They're really amazing, but they're just slightly less commonly used, so I ordered it this way. Kind of don't tell the PySpark people the best for last. And I can say that at PyData conference because this is also a Python Rust implementation. It's just the JVM I have a problem with. Oh, you know what? I think just the updating of the Jupyter Lab notebook finished, or didn't update because the cell is done. So the default vacuum operation was trying to vacuum files older than the default retention policy, which was 100 hours, and there were none because we just made these files. So it just didn't do anything. It did it very slowly. But here I set it to 0 hours, so that would be everything in the Delta table, including grid. I'm so sorry. This is where that safety mechanism catches us. It says, are you sure? That seems like a terrible idea. If you're not sure, why don't you use a value that's reasonable, like more than 168 hours? So it's looking out for you. It wants to make sure that you don't accidentally vacuum 0, thinking maybe like, oh, I'm vacuuming the 0th version, because that would be the first one. And you know, just knock out the entire table. Because this uses a time-based in hours cutoff for vacuuming. Oh, yes. Oh, okay. Gotcha. But we can turn that off and then we can just vacuum away and just destroy everything. Any questions? Yes.
If you're just doing append operations and you're, say, vacuuming old versions, will it still keep all your data, or is it going to potentially delete old file, like basically the old stuff from those?
Great question. So the question was, you're doing a vacuum operation, your version 0 that you're going to vacuum away is pointing to file 1, but so is your most recent version. So because a more recent version is pointing to that file, it's safe. Only the files that are kind of orphaned by recent enough versions are in trouble.
So the history in the Delta tables persisted forever until you run the vacuum operation, I guess?
Yeah.
Sorry, I missed that. Sorry. I was saying that the history in the Delta table is persisted until you run the vacuum operation?
Or even
That's correct, yes. So basically, all the history for a Delta table will persist because you're basically keeping multiple versions of the same Parquet files, and then there's a transaction log. Now, because the log is efficient, and because you're not doing a listing of files, because the files actually exist in transaction log, so you know exactly where to get them, so you're actually not doing a list on web APIs. This is basically what you have when you're getting a storage system like the cloud storage object store. It's actually just pretty efficient, and you can in fact store for a very long time. Now, the problem for doing that, of course, is that you're paying money. So we do advise you to vacuum, but we definitely have a subset of customers that keep many months, and in some cases years of history. Now, I don't think you should do it personally, because again, like usually it's more like you do it for like, I want for fiscal reporting resolution. And then what I would advise for those scenarios is like, well then just generate the fiscal report for the month, save that to a separate table, and then actually have to keep the whole history for that. The history for time travel for Delta Lake tables is really more about money, not really for that type of thing. So that's why you want to shorten.
Awesome. Thank you so much, everyone.
All right, let's get a round of applause to the